get this up to its maximum height of the day, I think. All right, thank you, everybody. It's great to see a full room of familiar faces and friendly botanists, of course. I'm always excited about this meeting, although I rarely come because I'm often in the field because it's in my hometown. I grew up in Chico. So I get to stay with my parents when I'm here, and it makes it a cheap conference. So I'm going to be giving, again, a pretty general talk today about sort of some thoughts I've had over the years on edaphic systems and their effect on plant evolution. This is sort of the subject of most of the research I do, although I've looked at a lot of various systems. I'm generally interested in adaptation, but I think soils have sort of constrained most of what I've looked at. So I'm always interested in how soils affect things. And I apologize for any issues with the text on this. I think when you convert from a Mac to a PC on the presentations, the text gets squashed. So we all know that chemically unusual soils have a powerful effect on plant life, whether you're talking about ecology, as in the assembly of communities, or their actual evolution. And you don't need to go any further than this spot in El Dorado County, where I did most of my dissertation, to see this in full force. So what we have here is a geologic disjunction between, basically a geological fault line between two substrates that couldn't be more different chemically. Gabbro in the foreground and a sort of shale type substrate in the background. And the transition goes from this very hard Adenostoma and Arctostaphylos chaparral to basically an oak woodland with a grass understory. And this occurs over the course of maybe about a 2-meter distance. And really there's just a handful of species that are shared between these two habitats, even though they're just a stone's throw apart. But it's a great example of this phenomenon because you have in the foreground a suite of endemic species that are basically, we think, speciated on the basis of this Gabbro soil compared to the non-Gabbros around. There's species that are restricted to this Gabbro locally that don't occur on any other local substrates. A lot of them are outside their range. And we also have just the formation of unusual plant communities, as you can see, that really don't share much in terms of their native plants. And so when I first saw this, my first year of graduate school, I was pretty much hooked. When I started traveling around California looking for more examples of this, I was seeing it everywhere. It's not, I was reinventing the wheel, of course, but it's something you go through in graduate school, rediscovering these amazing patterns. And it pretty much hooked me on soils because it was a way to link together a variety of evolutionary and ecological concepts with a sort of single system. We all need a system to study, whether we're studying climate change or a particular group of taxa, in a lot of cases for systematists. But for me, working in a department where I did my graduate work that was mostly evolutionary and ecological, much more question-driven, we needed a sort of a system that would generate good evolutionary and ecological questions. And edaphic systems are great for that. And you can pretty much go from the whole gamut of evolution and ecology with this system. So you can ask, at the very smallest scale, how do plants adapt to soil? And we're talking here about very small genetic changes. How do plants go from a plant that can't grow in Gabbro to a plant that can? A lot of plants are plastic, they can grow on and off, but most aren't. And so they need to acquire genetic differences from their close relatives in order to do that. And we can track those genetic changes. We can identify those genetic variants and figure out which ones give them the capacity to do that. And that's something I've been doing. One level up from that, I guess once a plant has become very much locally adapted, it could potentially speciate if there's enough of a selection gradient, or if it's isolated enough, you could have the evolution of a new species. And from speciation, of course, we start thinking about how plants migrate and form communities, and that's also constrained by soil. Some plants can grow on particular soils, for example, serpentine, others can't, and that pretty much constrains where we find plants. In addition to climate, of course, but if you can subtract climate out of the equation, a lot of the times you find that soils are a big factor. So my talk today is going to focus on soils that are in serpentines. But I want want to talk about serpentine because most of what we know about edaphic systems and the answers to the information we've learned about those things that I showed you in the previous slide, most of that's come from serpentine because it's a substrate that is very, very stringent chemically. It's poor in most of the nutrients that plants need. It's rich in most of the nutrients that plants don't need. And they often form very shallow soils. They're very, very tough. They're basically an extreme example of a chemically unusual soil. And from serpentine, you kind of go downhill in the gradient of stringency through soils that are tough soils, different soils, unusual soils, but not basically, in the case of serpentine, what is essentially a toxic soil in a lot of cases. And so a lot of what we know about these phenomenon have been learned in serpentine because it's so extreme that the reactions of the plants really are easy to study. They're obvious. I think I've put here kind of the three kind of key things I think we've learned in the last 50 years about how serpentine affects these three levels of evolutionary ecology, from adaptation to speciation to migration. And I think in the case of adaptation, one of the really interesting things we've learned is that when we go in and we try to look at these individual genetic changes that confer adaptation to serpentine, we find that they're, in many cases, convergent. They're completely different changes in different plant groups, even ones that are closely related. But they're also often parallel. We find that the same genetic pathways are upregulated, for example, highly active calcium transport or highly active metal transport. And so those are changes that have happened to the same genetic pathways, but they're not because the plants are closely related. They're because that's the correct pathway to modify if you want to become serpentine adapted. So those are two interesting ideas, that we get this mix of both convergent and parallel adaptations to what is really a challenge that is the same no matter where you are on serpentine, no matter where you are really in the world. At the level of speciation, one of the things I think has been very interesting to see is that, particularly with research out of Susan Harrison's lab, and Brian Anaker in particular, this idea that serpentine association is basically a trait that is sort of prone to rapid evolutionary change. And I mean rapid at the level of the resolution that we have phylogenetically at this point. I think when we go deeper, when we get better resolution on all these phylogenies, we'll find that it's maybe not as rapid as we thought. But basically the idea is that, at least in the case of serpentine, it's really not a dead end. Lineages that become very, very serpentine prone are capable of reversing back to non-serpentine. There's not really a high extinction rate associated. And so that's an interesting thing to look at. And we find this borne out in our large sort of plant genera in California that go in big for serpentine. For example, plants that I study like Ceanothus and Arctostaphylos. When you actually do get a phylogeny that's worth a damn, which is hard in those groups, what you see is that it's very labile. You get multiple evolutions of serpentine, potentially reversals. It doesn't seem to be the kind of thing that is associated with a particular lineage. It just pops up and blinks out. And finally, migrations. This is complicated, and you could really spend a lot of time reading very interesting papers about this. In general, what we've found with migration, in fact, particularly sort of disjunctions and plant community formation, is that the serpentine soils don't seem to contribute very strongly, at least when you're comparing them to climate. And we're talking here about regional diversity, so that in particular. So regional diversity is very much associated with climate as compared to serpentine. So this kind of argues against this idea of the super-edaphic diversity of the California floristic province being one of the main drivers of the diversity we have. It might really be climate, and that's why I say climate is king. So that's what we've learned from serpentine, but I want to go beyond serpentine to some of these other substrates. This is gray wacky, not gray wacky. I don't know why it does this. I think I just need to make the margins bigger on the text here. So some example substrates. I couldn't find a picture of some California sand dunes. This is from Colorado. But these are all substrates we have in California, and they all have effects on plant life. Very often when you visit outcrops of these types of soils, you find endemic plants, you find unusual plant communities. In many cases, it's not as extreme with serpentine. It's not something you can see from space, but it's still important. So the California floristic province is sort of the area where I'm focusing. We're talking about an area of high diversity and endemism with a Mediterranean-type climate. It's an unusually stable climate. We've found from a lot of research has confirmed this. It has a high topographic diversity and, of course, extreme soil diversity. Some of my recent research has just looked at this question of really how many are here, and as Jay said, it's about 37% endemism, down from 40. And about 20% of our CFP endemics, I'm still working on this number, but it seems like about 20% of them are associated with unusual soils. So we're getting a strong signal for this. And probably about 10% of these are serpentine, but the other substrates add quite a bit. And in these cases, we're talking about, for example, metavolcanics in Southern California with a lot of endemics, a lot of unusual endemics on the Sierra Nevada batholiths, like the Mimulus laciniatus we were just hearing about. Local example, basalt on Table Mountain with a lot of neat wildflowers and some plants that are locally unusual. And then sandstones in Southern California. So to answer this question, is soil specialization really an evolutionary dead end? I would say that the answer, and I'm going to sort of do this in reverse order, give you some examples after stating the answer. And I think it's mostly no. In most cases, it's either a neutral factor or a driver. And I think that I'm going to try to make this argument, but I'd love to hear back from people later in the conference. So at the level of adaptation, the hypothesis I propose is that local adaptation probably boosts the resilience of the species as a whole. So if you have species that can adapt to different types of soils, that's going to make the species more resilient to climate change, to really many different types of perturbations. And we have a great example in the case of multiple origins of copper-tolerant seed monkey flowers. So these are a species, basically the widespread seed monkey flower, that's been able to adapt to copper over and over repeatedly. And it's sort of given it a lot of resilience on these copper outcrops, basically old copper mines, because it's really done it in a kind of different way in each case. It's not that it's gotten the same exact genetic change, it's sort of redone it over and over. So that's an example there. Another great example is from a little bit of my research on Streptanthus insignis. We went into this thinking that we were mostly going to find sort of serpentine, real strong associations with serpentine. But what we actually found is that gray wacky was an important substrate as well. And the plants did have particular adaptations to that soil. They weren't as strong as the serpentine, but when you grew the plants, you could really see a strong signal for that, that there was a response to the soil in greenhouse. At the level of speciation, unusual soils other than serpentine can act as drivers of speciation, and Streptanthus is another great example of this from Sharon Strauss and Eva Lukash's work. And they basically found that barren soils have been kind of the major promoter of diversification and speciation in Streptanthus, and sort of the precursor to a lot of these unusual types of soils that they've inhabited. And so it's not just a serpentine story, it's a barren soil story. And when you say barren soils, you're often talking about these unusual types of soils I was alluding to before. A little bit of my research on Gabbro, another speciation example. These Gabbro soils seem to have been able to both promote and sort of reinforce the speciation of a Gabbro endemic species of Ceanothus. And it's a great example of a very similar situation to serpentine, but on a pretty different soil chemically. Finally, migration. The hypothesis here being that unusual soils are able to harbor plants far outside of their normal climatic limits. And some of the research I've been doing recently on this is in the Pebble Plains, the San Bernardino Mountains, where you get basically what looks like an alpine flora, but at an elevation up to 1,000 meters below where it would normally occur. And the idea here, of course, would be that you might have these alpine plants persisting way outside their normal climatic limits, which would give them much better resilience to future climate change, and probably climate change in the past. Another interesting example from Baja that I've just been starting to look at, I know this is NCB, and Baja's not part of Northern California. But this is a cool spot, and there are examples of this all over the state, where you have these weird soils that support these populations of plants. In this case, it's bishop pine, and it's way outside its climatic zone here, but it seems to grow there on these very weird acidic volcanic soils. And so I'm just started a project to try and look at that and figure out, is that really what's happening? And so that's it for my talk. And I think I have time for questions.